Okay, everybody, I did this and then it deleted, so now this is like my second rodeo, but welcome to Chapter 6, an introduction to metabolism. So this is going to really put enzymes to work and introduce us to the overall idea of cellular respiration, where we break down our food to get energy, as well as photosynthesis, which is the process of taking the sun and using that as energy to fuel the creation of food. If we remember to the enzyme part, we oftentimes, or the body or cell oftentimes, breaks reactions down into multiple steps. And that's really a quality control for the cell because it's not just an A to B. So there can be a lot more added in regulation if you can do that. Metabolism as a whole is just the sum total of all of an organism's chemical reactions. So it includes all of the breaking of things down as well as all of the building things up. And so it is the manage of the materials of energy resources of an entire cell in its entirety. And there's, thousands, hundreds of thousands, maybe even millions of different reactions happening. The two types are catabolic and anabolic pathways. So catabolic are the ones where you're actually breaking something down. Energy is being released because you're breaking something down into smaller bits. So breaking down your food to energy is a catabolic process. For me, I always think I don't like cats. Sorry. So I always think of that as a breaking down. Someone else used the idea of the heavy machinery equipment, the yellow ones that say cat on the side, as a way to break things down. Anabolic pathways are building things up. So they, I don't have a fancy way of remembering it, but it's the opposite of catabolic. So they are putting things together. This unit is going to kind of touch on chemistry again. So this is where energy comes in. You could also say it's physics. But energy in and of itself is just the capacity to do work. And there's different kinds of energy that you can have. In our case, we're going to talk about kinesthetic energy and potential energy. Kinesthetic energy is associated with motion. Kinesthetics or kinesthetic learners need to be moving around. And that's usually how I remember motion. Heat is a thermal energy, but it often influences kinetic energy. It increases the movement of the things around it and kind of provides kinetic energy by its nature. Potential energy is something where there is energy stored, whether it's due to a position, so that's kind of the physics take, something that's higher in the air has more potential, or it could be a structure. So in a biological sense, complex carbohydrates or fats or things like that store energy inside of them so that they have the potential to release that energy when we break them down. Chemical energy, as I mentioned, that's the biological sense, is the energy available for release when a chemical reaction takes place. So when we break down or use up ATP, for example. Energy, it can be converted from one form to another. So if I wanted to turn chemical energy into mechanical energy and then into electrical energy, for example, it can kind of be converted into multiple ways. This graphic kind of puts that together. So the diver at the top, he has the most potential energy on the platform, in this case because of his height. And if he starts diving, we are now converting that potential energy into kinetic energy as he moves. And as he gets lower and lower and lower, that person gets less and less potential energy because they're kind of using it all up. And then if you put in energy, essentially to climb back up again, then you are regaining your potential energy. So you got to put in the energy to regain that potential store of energy. Thermodynamics is a general term for the studying of those energy transfers between one thing to another. There are closed systems, but that's really not normal. A closed system in and of itself is totally isolated from its surroundings. So liquid in a thermos, for example, in a sealed container, nothing is getting in, nothing is getting out. So all of the energy is remaining really in that container. And so it's a closed system. However, an open system is where energy is transferred between the system and its surroundings. Things go in, things go out. We as organisms are those open systems. You know, we eat food, things come out of us. We breathe in air, we breathe out CO2, those kinds of things. Open system. There's two major laws of thermodynamics. The first one has to do with conservation of energy. It's important to know that energy is not created or destroyed. The amount available in the world, or universe for that matter, is totally constant. It can't be created or destroyed. Again, it can be transferred from one organism to another. So if a bear eats a fish, for example, it's transferred to the fish and really transformed. So it might be mechanical energy or something else turned into chemical energy later. The second law of thermodynamics is that every energy transfer that occurs or transformation's path is to increase entropy of the universe. Entropy is kind of a measure of randomness or disorder. Things get more disorganized or more full of disorder as you perform chemical reactions or transfer energy. During this, sometimes things are given off that are not really usable. So it's not to say that it's destroyed, because it's not, and that would go against the first law of thermodynamics, but it's transferred into heat. We can't use heat. In this instance, the bear is giving off heat as it is breathing out CO2 and water, which is kind of an overall break what is happening when he's breaking down the fish that he ate in the previous slide. Holy vocab. So free energy is the amount of energy that is available to perform work. In this case, I think of it as kind of the amount of potential energy that it has. Free energy to do work, the potential to do something. Exergonic reactions. Think exit. Those ones are giving off energy or releasing it into the surroundings. Endergonic, think endo. Endo means inside. So endergonic reactions require energy. You have to put that in. Exergonic, give off, and those ones are spontaneous. They just happen on their own. And since they're giving off energy, their free energy change is negative, meaning that they are losing further potential to do work because they're giving all their energy away. It's kind of like when you guys are drained at school. You give all of your energy away, and now you're in the negatives and need to get it back before you can do anything else. Endergonic reaction means energy is required, so it has to absorb free energy or take in energy. And as you add energy to the system here, that free energy goes up and it becomes positive, something greater than zero. This picture just kind of shows you a graphic of that and how that happens. Things are always going from less random to more random, or moving, shifting, going from a less stable overall to a more stable overall. So like these things, for example, I'll just look at A for right now, has a lot of free energy. This person is high up. They have a high potential of free energy. It's not super stable because this person could probably blow over at any minute. And that high energy is kind of uncomfortable. It wants to go down to its happy, low, steady state after a time. But it has the high capacity to work. And then under spontaneous change, then this person would kind of start to fall, like in this picture. And then it's going to be more and more and more stable. And then the released energy, so whatever energy was given off in this process, can now go and do work. And then eventually it gets down to the bottom where it's the most stable, the most happy, but there's less ability to do any kind of work. Here's what this looks like in a chemical reaction kind of way. So in an exergonic reaction, energy is given off. The reactants have more free energy starting than whatever products are made at the end that has less free energy. And you can see energy is released. So however much total energy that is, it's going to be something that's going to contribute to a negative free energy. That's the amount of energy that is given off or released in the equation or in the reaction. And then whatever the products have left are kind of whatever energy is still within that molecule. An endergonic reaction is pretty much just the opposite. So reactants down here, products have a higher energy. So at some point energy was put into this system, and you can see that that amount of energy then would make the Gibbs constant positive. A living cell is never at equilibrium. So it's important to know that. We talked about it before when we talked about isotonic solutions with diffusion and osmosis. When things reach an equilibrium, it doesn't mean things just shut down and stop. There's still movement back and forth. It's just not a net movement of sorts. The cell can overall do three main kinds of work. It can do mechanical work, so bending, shifting, moving. It can do transport work, and you know that already from cells moving pieces around through the endoplasmic reticulum and the Golgi and vesicles and all of that. Chemical, so if there's certain signals or signaling pathways that the cell needs to do, it can do chemical reactions, or neurotransmitters are an excellent example of things like that. Cells manage energy and resources to do work really by trying to couple correct reactions. They try to put an exergonic reaction that's going to give off a certain amount of energy with an endergonic reaction that's going to absorb roughly that amount of energy, so that it doesn't really end up wasting any energy or output. That's what energy coupling is. ATP, as you know, is kind of the currency of the cell. That's what the cell uses as one of the major energy sources. It's not the only one, but it's the main one. And it's made by our friend, the powerhouse of the cell, the mitochondria. But this is what it looks like. And I'm going to show you why it's considered the main energy source. There's adenine. So your A, T, C, and G from DNA. Adenine is right here. It's attached to a ribose sugar, which we've learned about previously. And then there's phosphates. In this case, there's 3 phosphates, so it's called triphosphate. Adenine triphosphate. And there is energy that is in the structure of these phosphates, so that when you remove a phosphate, energy is released in that process. It's going from higher energy levels or a less stable state of super high free energy to a lower, more stable state of less free energy. So here's kind of what that looks like. So when these bonds are broken by hydrolysis, we've learned that before, hydrolysis, to break with water, energy gets released. So when you chop off a phosphate, energy comes off the side. This release comes from a chemical change. So it's not to say just breaking that bond magically makes energy pop out, but really it's a chemical change. When there is a lower energy level, things have gone from a high to a low, and that result has left as energy. In terms of how ATP performs its work, exergonic reactions release the phosphate. So in an exergonic reaction, you have ATP, which is kind of stored energy, and it chops off the water and releases energy. And by chops off the water, I totally meant chops off the phosphate using water. It releases energy, and that ADP molecule doesn't just go away, it can be recycled. So then later on down the line, these ADPs can have a phosphate stuck back onto them. And these are energy from catabolism. So things that have broken down in other areas are giving off energy. And the energy that's being given off in the cell by other catabolism events fuels basically the sticking back on of a phosphate onto ADP to make it ATP again. And so you've kind of recreated this using energy from the cell. And now it can store that energy and use it when it needs. One example is transport work, so ATP phosphorylating transport proteins. In order to make this happen, we are going against the concentration gradient, so this is active transport. It needs to be fueled by ATP, so that phosphate helps it bind, and once it moves through, that energy is given off because a phosphate has been chopped off. Later we'll also find the ATP proton pump that makes ATP as something similar. And then down here, this is really a muscle example. If you have a nat and phys, the sliding filament theory is really what this is. So you have troponin, tropomyosin, actin-myosin, all of that business trying to contract with all the different motor proteins. And ATP really facilitates kind of the sliding part of the sliding filament theory. It allows certain things to move over and slide and kind of recock in the position that it needs to be to happen again. So that requires ATP to happen. The last couple slides really are just recapping what enzymes do. So this was really covered in your previous slides, but I just wanted to leave them in there as an extra review. But enzymes are really the catalysts that are making metabolism happen. There are ACEs that are providing speedier chemical reactions, and we learned that their job is to speed up chemical reactions, and they do that by lowering the activation energy. This picture shows a good view of that. So the black is without an enzyme and the red is with an enzyme. It's important to note that the reactants and the products are ending up in the same exact space. So there's really no change in free energy. What it is doing is it's lowering the overall amount of energy that it takes to get over that hump. It lowers the amount of energy you need to put in to make the reaction go. And so by doing that, it actually makes it go faster because the cell or whatever doesn't have to put in as much time to accumulate that much energy. And we've already learned about the substrate and the enzyme substrate complex when they come together, and they do this at that magical active site. And when they come together, they form an enzyme substrate complex. Then the enzyme basically does its job and releases the substrate. The enzyme itself is reused. It is unused at all in the reaction. Now it's going to go off and find new substrates to continue this process. Catabolism, to break things down. So enzymes do have an ability to chop things into pieces or break them down if needed. They can do anabolism too. So it is possible for enzymes to actually fuse things together. And then lastly, feedback inhibition. So this is again where later on down the stream components have the ability to inhibit upstream components as a way of acting in regulation for the cell. So that'll about do it for overall metabolism.